Swayam Prabha. Digital India. Educated India.
In the previous lecture, we were discussing about the finite element formulation of Euler-Bernoulli beam. We discretized the beam into a set of elements. The total number of elements was NE, and then we did the elemental formulation, and we ended up getting a set of coupled ordinary differential equations, which we call elemental finite element equations, and that equation consists of mass matrix, stiffness matrix and force vector. So, today we will start from there. Now, for this problem, for the case of Euler-Bernoulli beams, the mass matrix, the explicit expression for mass matrix looks like this. And then we have 11 LE square by 210, 9 L by 70 minus 13 LE by 420, and here we have 11 LE square by 210 LE cube by 105, 13 LE square by 420 minus LE cube by 140. So, if I do the integrations over the elemental length, that I get as an expression for the mass matrix, and then we have 9 LE by 70, 13 LE square by 420, and then 13 LE by 35, and minus 11 LE square by 210, and then here we have minus 13 LE square by 420 minus LE cube by 140 minus 11 LE square by 210, and the final diagonal term is LE cube divided by 105. So, this we get after doing the integration, and as we can see that this matrix that we get is a symmetric matrix. Now, the symmetry is there in stiffness matrix also. The stiffness matrix that we get is this. We have the stiffness matrix that comes is, we have EI sitting outside, then 12 by LE cube, 6 by LE square minus 12 by LE cube, and then again 6 by LE square, and then we have 6 by 6 divided by LE square, then the diagonal term we have 4 by L, and then minus 6 by LE square, and 2 by LE L, and then minus 12 by LE cube minus 6 by LE square, and then in the diagonal term we have 12 by Le cube and minus 6 by Le square, and in this term again it is symmetric. So, it is 6 by Le square, this is 2 by Le and again minus 6 by Le square, and finally, in the diagonal term it is 4 by Le. So, this is our expression for the stiffness matrix, and again this is possible only when our rho A and EI they are not varying across the domain. So, at any x, so EI and rho A, if they are functions of x, then they also gets integrated and I may not get this expression. Then if I assume that my Pz is constant, then so instead of calling it K E I, we just call it the entire K matrix, and there is a generic definition for Kij which we will see, and similarly this is also F, and we look into the generic definition of F. So, F the force vector becomes Pz, and that is multiplied with Le by 2, Le square by 12, Le by 2 minus Le square by 12. So, here Mij in general is defined as 0 to Le rho A N1 Nie multiplied by Nje dx, and Kij is defined as 0 to Le Ei Ni comma xx Nj comma xx dx, and Fie is 0 to Le Pz Nie dx. So, when Pz, Ei and rho A they are not functions of x, they can come out of the integral sign, and rest of the term on being integrated give me this matrix and this vector. So, now that we have found out the elemental equations, we need to find out the global set of equations. So, to do that, again let us remember that we had divided the entire domain into a set of elements going from x equal to 0 to x equal to L, and each of these element has two nodes. The nodes that are at the two end of the structure, they are not shared by more than one element, whereas the intermediate nodes are shared by two elements. Accordingly, we defined our degrees of freedom. We had D11, D21, D31, D41, then D12, D22. Now, this point cannot have more than one displacement, otherwise the displacement continuity would not be there, which means that D11 and D12 they should be same. So, D12 is equal to D31 is equal to some value, we call it D2, we will see that, and similarly D41 is equal to D22 is equal to some value. So, that brings us to another nomenclature of the degrees of freedom. So, these nomenclatures where I have a superscript, they are with respect to some element. Now, I put another nomenclature which is with respect to the entire global system. So, globally this is the first degree of freedom. So, it is D1 first node first degree of freedom. So, it is D1 and then D2, Then globally I have after that D3, D4, D5, D6, D7, D8 and we can go on. So, finally, I will have D 2Ne plus 1 and D 2Ne plus 2. So, we can say that D12 is equal to D31 is equal to D3 and D22 is equal to D41 is equal to D4, and accordingly this node also will have nomenclature with respect to elemental definition, the degrees of freedom at this node. So, we have D32 and D13 they are same and they are equal to D5. Similarly, D42 is equal to D23 they are same, that is equal to D6. Now, we have seen the force terms also. So, if I look at the force terms, this we are drawing it once again here. So, we have the node specified. So, that one place does not get crowded. So, we are drawing it separately. So, here we have F11, F22 and F31, F41. The second one is not F22, it is F21. Similarly, F12, F22, F32, F42 and again this has F13 and F23 and the nomenclature can go on. We have seen that there are 4 degrees of freedom and accordingly there are 4 components of the force vector also. So, that is what we are writing here. So, each element has 4 component of the force vector and again they are local numbering of the force vector. So, globally I can call them F1, F2, F3, F4, F5, F6 and so on. Now, F11 is globally F1, F21 is globally F2. However, F3 is globally a combination of F31 plus F12. Similarly, F4 globally is a combination of F41 plus F42. So, here this force that I get from the element number 1 and this force that I get from element number 2, the adjacent element, on being added they give me the force F3. So, F3 is F31 plus F12. Similarly, F4 is F41 plus F22 and accordingly we can say F5 is equal to F32 plus F13 and F6 is equal to F42 plus F23. So, now combining all the equations. So, now we have the finite element equation, the 4 by 4 system from the first element and the 4 by 4 system from the second element. Then we can in the equation for the first element we have terms like D31, D41, we can instead of calling them as D31, D41 we can call them by their global number D3, D4. Similarly, in the second equation also we have in the second finite element equation set also we have D12, D22 and instead of calling them as D12, D22 we can call them as D3 and D4. And similarly, we have force and we can add up the forces and finally, after adding up. So, if I look into the first elemental equation we have M11 or if I look into the first elemental equation we have M11 of 1 multiplied by D1 double dot. So, we are writing the degrees of freedom in terms of the global number and then we have M12 D2 double dot and then plus we have M13 D3 double dot plus M14 D4 double dot plus K11 D1. These are all mass matrix corresponding to the first element, and that is equal to F11 of on 1. Similarly, I have the second equation which I am not writing. Then the third equation is F31 multiplied by D1 double dot plus M32 multiplied by D2 double dot plus M33 of 1 multiplied by D3 double dot plus M34 of 1 multiplied by D4 double dot plus we have K31 D1 plus K31 of 1 D2 plus K33 of 1 D3 plus K34 of 1 D4 is equal to F3 of 1. And similarly, M41 D1 double dot M42 D2 double dot plus M43 of 1 D4 double dot plus M44 plus we have M44 of 1 D4 double dot, and then we have K41 D1 and then we have K42 of 1 D2 plus K43 of 1 D3 plus K441 of 1 D4 is equal to F4. Please understand the second equation was not written, but that equation exists. So, that was the 4 equations from the first element. So, first element. Now, if I write the second equation from the first element, the equation would look like this: M11 of the second element multiplied by D1, no it is not D1 now, it is D3, because D1 of second element is globally D3, plus M12 of second element multiplied by D4 dot plus M4 of M3 of second element multiplied by D5 dot plus M4 of second element multiplied by D6 double dot. These are all double dots, plus K11 of second element multiplied by D3 plus K12 of second element multiplied by D4 plus K1 of second element multiplied by D5 plus K13 of second element plus K14 of second element multiplied by D6, and that is equal to F1 of second element. Now, we can see that if I, so this comes from the second element. Now, we can see that if I look at this equation with the third equation from the first element and the first equation from the second element, these two equations have D3 and D4 as common terms, and if I add these two equations in the right hand side, F31 and F12 gets added and they give me a fourth term F3. So, if I add third equation of first element and first equation of second element, that gives me M31 D1 double dot plus M321 D2 double dot. Then when I am adding this term and this term, the mass terms get added and I get M331 of 1, M33 of 1 plus M11 of 2, they gets added and they are multiplied with D3 double dot. Similarly, here I have D4 double dot and here I have D4 double dot. So, M34 of first element and M12 of second element gets added and that gives me M34 of 1 plus M12 of 2 and I get that summation multiplied by D4 double dot. Then I have these two terms, they do not get added to anything, M32 D5 double dot, M13 of 2 D5 double dot, M14 of 2 D6 double dot. Likewise, I have the stiffness terms here and they also gets added and that gives me K1 1 of 1 multiplied by D1, K3 1 of 1 plus K32 of 1 multiplied by D2 plus K33 of 1 plus K11 of 2 multiplied by D3 plus K34 of 1 plus K12 of 2 multiplied by D4 plus K13 of 2 multiplied by D5 plus K14 of 2 multiplied by D6. At the right hand side I have F3 of 1 and F1 of 2 added. So, I have F3 of 1 plus F1 of 2. So, likewise I can add the fourth equation from the first element and the second equation from the second element and they also show equation like that. In that way the intermediate equations can be added and a global system of equations can be formed and that system would be of size 2n plus 2. So, finally, the global system of equation is formed and the formed system, the global system of equation looks like 2ne plus 2 multiplied by 2ne plus 2. Then the global displacement vector which is of size 2ne plus 2 multiplied by 1, I have a double dot here, then plus the global stiffness matrix again 2ne by 2 multiplied by 2ne plus 2 multiplied by 2ne plus 2 and that is multiplied with a d vector, the degree of freedom vector which is of size 2ne plus 2 multiplied by 1 and that is equal to a right hand size force vector which is of size 2ne plus 2 multiplied by 1. So, that is our global finite element equation and then after that we can put the essential boundary conditions. So, for example, if I have a cantilever beam like this and in that case this is the fixed end means the displacement and slope is 0 at this end, which means our D1 and D2, the global boundary conditions D1 and D2 are 0, because we saw that we have discretized into a lot of elements. The first degree of freedom globally is D1 and D2, the first one is the displacement, the second one is the slope. So, these two quantities are 0 and that is our essential boundary condition. So, in this case I have to then apply the essential boundary condition. To apply the essential boundary condition, what I do is I remove the first row and first column from both M matrix and K matrix, and that is how the system is reduced to a 2n E by 2n E system, because our D matrix is of size 2n E plus 2, and the first 2 degrees of freedom are already known to me, they are 0. So, I do not need to calculate them. So, I have to deal with only rest of it. So, starting from the degree of freedom D3 to the last degree of freedom I have to deal with. So, I cancel the first row and first column of the mass matrix, of the stiffness matrix and the force vector, then finally, I get a reduced set of linear simultaneous ordinary differential equations after applying the essential boundary conditions and the boundary condition is d1 equal to d2 equal to d1 of 1 equal to d2 of 1 equal to 0, and if they remain 0 always, that means that d1 double dot d2 double dot d1 of 1 double dot d2 of 1 double dot always remains 0. If then we set them 0 and we remove the corresponding rows and columns from the mass and stiffness matrix, and then we get a reduced set of equations of size 2 n E by 2 n E, and that gets multiplied with a D matrix of size 2 n E by 1 plus K 2 n E by 2 n E, and that gets multiplied with the D vector of size 2 n E plus 2 n E by 1, and then I have the force vector 2 n E by 1. Now, this set of equations I can solve. So, if my force is a time dependent force, then we can solve this ordinary differential equation. We have already discussed various techniques to solve the ordinary differential equations, and within using that we can find out D at each and every time step. If we are interested in finding out the eigenvalue of the system, then we can set, then we do not need F, then the force vector is 0, and then we can solve the eigenvalue problem considering M and K, and that would give me the natural frequency and mode shape of the system. So, this is about the finite element formulation of the beam, and so this formulation was useful to understand the formulations that are given in the paper that we are going to discuss for analyzing a beam which has shape memory alloy fitted to it. So, with that I would like to conclude the lecture here. Thank you.